Alright, so here we have the first question, that is from the topic of measurements and electricity. A student measures the resistance R of a lamp for different values of the potential difference across it. The student connects the circuit as shown in figure 1.1. The student closes the switch, reconnects the crocodile clip. This one is your crocodile clip at the length 10 centimeter of the resistance wire. So whatever the length of the resistance wire was, he chooses only 10 centimeter of it. So the crocodile clip is connected at the 10 centimeter mark. Figure 1.2 shows the reading on the voltmeter and the ammeter. Okay, the student repeats the procedure with different lengths of the resistance wire. Results are shown in the table. Recording table 1.1, the values of V and I. Okay, so we can just look at the data here. We can look at the scale and we can get to know the reading from here. So you see you have 1 2 3 4 5 6 7 8 9 10. You have 10 lines, and then those 10 lines make up 0.5. So that means after 2 lines you'll be getting 0.1. So you'll be having 0.1 here. Over here you'll be having 0.2. Then you'll be having 0.3. Over here you'll be having 0.4, and only then you can have 0.5 after, for example, 0.5. Then how many lines are there? There were 10 lines. So what does that mean? It means each line is representing 0.05. One line represents 0.05. 2 lines would represent 0.1. This is a mathematical way, but you can just use common sense there. You see 10 lines are making up 0.5. So 2 lines would make up 0.2. So the reading on the voltmeter is 0.2. I can write it over here. And let's check out the reading on the ammeter. Let me zoom it. So for the reading on the ammeter, so you have 0.5 here, and then that would be 0.1. This one would be 0.2, 0.3, 0.4, and only then we can have 0.5 over here at the 5th bigger line. So that means each big line represents 0.1. So we are one small line behind 0.1. So since we are at the 9th line, so this one would be 0.09. Alright, so this is the easiest part of it. There are plenty of ways you can analyze the scale and read from there. So for this one we have 0.09. I can write it over here. Part B. Complete the top row of the table 1.1 by calculating the resistance of the lamp when length equals to 10 centimeter. Use the equation shown. R equals to V over I. Okay, in ATP you're provided with these kind of formulas. All you have to do is to insert the values and get the right answer using the calculator. So R equals to V over I. So what you have to do is 0.2 divided by 0.09. What do we get? The next one is the student forgets to write in the current value for length equals to 100 centimeters. Calculate the current and write its value in the table 1.1. So you gotta refer, once again you gotta refer to the same formula, R equals to V over I. So for the length, when the length is 100 centimeter, the value of voltage is 2.5, the resistance is 11.1. You need to use the same equation to find the value of current. 0.2, sorry, not 2.5 divided by 11.9. What do we get from here? Let's move on to the next part, part C. The student examines table 1.1 and state that the resistance R of the lamp is directly proportional to the length. So this is what the student is saying, that the resistance is directly proportional to length. State if you agree with the student's statement. Justify your answer by using the values from the table 1.1. So if these two quantities are directly proportional, then that would imply that the ratio of these two would be constant. Okay, for example, I say in mathematics we study this thing, x, quantity x is directly proportional to y. Then you can convert it into equation. If you know a certain constant here, then that becomes an equation. So if x is directly proportional to y, you can write it as x equals to ky. And then if you shift y on the other side, then the ratio of x and y should have been constant. So meaning if you increase one thing, the other thing should also increase by the same proportion. So the overall ratio would remain constant. Is that the case here? So what you can do is you can find the ratio of length, resistance to length, for some of these values. Ideally you should be finding for all of them, but if there is a single value in which the ratio is not constant, that would mean that these two quantities R and L are not directly proportional to each other. No, we don't agree with the student's statement, and the justification is the ratio of resistance to length is not constant. If the question is, the student says that R is inversely proportional to length, check from the table if you agree with the answer or agree with the student's statement. How do we check then? If the two quantities are inversely proportional, keep it in your mind, then the product of these two quantities would be constant. So I can write over here, for quantities which are in direct proportion, and the quantities which are in inverse proportion. So if the quantities are in direct proportion, then the ratio of the quantities should be constant. And if the quantities are in inverse proportion, then the product of the two quantities should be constant from the table. Okay, you can check it from the table. And the two quantities are directly proportional. You can also check it from the graph. If the graph is a straight line, if they ask you to verify from the graph, then the graph has to be a straight line and the graph has to be passing from the origin. So if they ask you to find out if two quantities are direct proportion from the graph, then you check for these two properties. If they ask you to check it from the table, then you check for this one. And matter of fact, on a broader perspective, these two things are just the same. Anyway, let's move on to the next one. On the grid provided in figure 1.3, plot the graph of R on y-axis and V on x-axis. Start both the axes from the origin. So we are left with no choice. We have to start from the origin, and that would make it easier though. So this one would go on the y-axis, and this one would go on the x-axis. So we need to start from the origin. Let us plot the x-axis. Let us scale the x-axis first. The graph question is generally of 4 marks. The first mark is for labeling the axis. So I'm going to label the axis first. So this axis is representing voltage, and the voltage is being measured in volts. On the x-axis we have voltage or potential difference, V, represented by V, and the unit is also V, which is volts. On the y-axis we have resistance labeled as R, which is being measured in ohm. So R/ohm for the y-axis, R/ohm. So you write this thing, you get 1 mark from the graph question. Then the next one is to scale the axis. Now in order to scale the axis, you have to look for the maximum values that you have. For example, on the x-axis we are going till 2.5. So what if I do it like this? 0.5 here. After next 10, we'll be writing 1.0. After next 10, we'll be writing 1.5. After next 10, we'll be writing 2.0. After next 10, we'll be writing 2.5. Scale the y-axis. On the y-axis, the maximum value is 11.9. Let's call it 12. So what if I do like 2, 4, 6? Let me check it out. 2, 4, 6, 8, 10, 12. Yeah, we'll be pretty much good with it if we write 2 after 10 small blocks. Okay, so you have scaled the axis, and scaling the axis is the most tricky part. Once you are done with the scaling the axis, you get the second mark from this question, this 4-mark question. Okay, after that you need to plot the values. Okay, you need to plot the points, you need to plot the values. Like for example, the first one is the value on the x-axis is 0.2. So the first point is 0.2 against 2.2. This would be the first point. The second point would be 0.7 against 5.4, and then 1.2 against 8.6. Okay, stuff like that. So the first one is 0.2 against 2.2. 0.2 against 2.2. Okay, so after 2 blocks, what do we have? We'll be having 0.1. Okay, so let me just change the color here. So this one would be 0.1. This one would be 0.2, 0.3, 0.4. Only then we can have 0.5 at the 10th line. So for 0.2, we'll be at the 4th line. On this line, we'll be having 0.2. Against 0.2, we were having 2.2. So this one is 2. And in the middle of 2 and 4, we'll be having 3. It means after 5 lines, we'd be having 3. 1, 2, 3, 4, 5. So we'll be having 3 here. But what about 2.2? One small line after 2 would be representing 2.2. Only then we can have 3 at the 5th line. So 2.2, 2.4, 2.6, 2.8, and only then you can have 3 here. So 2.2 would be over here. So this is a point, 0.2 and 2.2. Okay, so this is a most time taking process, and it pretty much depends on your scale also. Like if your scale is kind of easy, your scale is not too dramatic, you'll be able to plot the points easily. And the question that they have asked you to draw a smooth curve of best fit. Alright, so I tell the student that this is the most advanced variation of all the graphs. If you're asked to draw a smooth curve of best fit, it is certain that you'll be making plenty of guesses before you're able to actually draw the correct one. So smooth curve of best fit is a curve that is showing the trend of the points, plus if there are certain points are not on the curve, not on the smooth curve, then the number of points scattered below and above the curve should be equal. Or there should be equal number of points below and above the curve if all the points are not exactly lying on the curve. For example, if I try to join these points with the help of a curve, then you realize something, that if we join them with a curve, then this curve would not be a smooth curve. Smooth curve means you draw a single arc with a single movement of your hand, and there should be no change in the direction. Okay, if your gradient is being decreasing, then it should decreasing continuously. For example, if I draw a curve like this, it is not a smooth curve because the gradient at this point was high, and then over here the gradient is decreasing. Okay, so far so good, the gradient is decreasing, but what happens after that is the gradient once again starts increasing. So the trend is not same. If the gradient is decreasing, then it should continue to decrease. Otherwise, it would not be a smooth curve. So this is now the most important part. I'm going to draw the smooth curve, and it would be an approximation because here it's not easy for me to draw. When you're drawing on the paper, it is slightly easier. So I have 1 point above the line and 1, 2, 3, 4 below. Sorry, 4 above the line and only 1 below the line. So let me draw it again. So for this one, I have 1, 2 points above the line and 1, 2 points below the line. Yeah, so that one is pretty much a good approximation of the smooth best fit curve. So we are done with this one. The line has to be a smooth one. They generally deduct the marks for this one. Okay, so the line has to be a sharp and smooth line or curve, whatever you have. Okay, anyway, now we have to answer some of the follow-up questions. So this one says, using your graph, describe how the resistance of the lamp changes as the potential difference V cross it changes. So as V increases, you can see the resistance also increases. But the thing is, they are not increasing proportionately or proportionally, so they are not in direct proportion. Okay, so there is just a general trend that if you increase the resistance, the voltage would increase, but the amount by which the voltage increase is not fixed. It is increasing kind of randomly. So increasing the resistance, the voltage also increases. And if we check, the gradient was higher. Initially the gradient was higher, and then the gradient starts decreasing. So you see in the yellow shaded part, the gradient is has been decreased compared to the previous gradient. So initially, increasing the resistance, the voltage was increasing by a great amount. Afterwards, once you were increasing the resistance, then voltage was being increased, but it was not being increased by the same great amount. This is what we call the rate of the increase. So the rate of the increase of resistance, sorry, the rate of the increase of voltage decreases. Important one. Let me explain this one over here. So you have, let's say you have resistance here and you have voltage here. Resistance being measured in ohm and voltage being measured in volts. And let me draw some of the points here. So first the resistance was 10, then the resistance was 20, then 30, then 40. So when the resistance was 10, the voltage was 10. let's make it a little bit different. The voltage was 5. When the resistance was 20, the voltage was 10, and then it was 15, or less 12, and then it was 13. So what do you see? Initially the change was plus 5, and then the change was plus 2, and then the change was plus 3, plus 1. So your voltage is being increased. You see, your voltage is being increased, but the rate of increase of voltage has been decreased, because first the change was, there was a great change. There was a change of 5, and then there was a change of only 2, and after that, afterwards, there was a change of only 1. So this is what this statement represents. So this is, I've written just for the example. The red line, the rate of increase of voltage decreases. It can mean something like this. Okay, these values are assumed value. If you want to refer to the actual values, you can take a look at the table. And we have the last part of this one. We'll finish it over here. Another student makes changes to the circuit shown in figure 1.1. She uses a variable resistor to vary the current and potential difference instead of resistance wire and the crocodile clip. Complete the circuit diagram in figure 1.4 to show how this is done. So we need to connect a variable resistor. One mark is for the symbol of the variable resistor, and the other mark, the second independent mark, is for the position. So the symbol and the position, if both are correct, then you'll be getting 2 marks for this one. Question number 2. A student determines the acceleration of free fall by timing the oscillations of a pendulum. The pendulum is shown in figure 2.1. It is clamped to a stand, as you can see in figure 2.1. The very first part is, on figure 2.1, measure the length small l of the pendulum in centimeters to the nearest millimeter. Centimeter to the nearest millimeter means your answer would be in centimeter. You read the scale in centimeters of your ruler, and you have to write the answer to 1 decimal place. For example, you write it as 3.3 centimeter. So you have 3 centimeter complete, and this one 0.3 represents nearest millimeters. Once you do it on the sheet of paper, it would have been 3.5. Okay, so sometimes the answer can be a little bit different on your sheet, because some of the orientation, the magnification of the paper is changed due to printing and stuff like that. The sheet of paper provided by the Cambridge, the question paper, it for 3.5, 3.5 centimeter. Okay, anyway, part B. Figure 2.1 is drawn 1/8 actual size. That means whatever the actual size was, this diagram is representing only 1/8 of that. The 8 is being compressed 8 times. It's been diminished 8 times. Length L, the capital L, is the actual length of the pendulum. Calculate capital L. So that means this length was reduced by a factor of 8. So what would have been the actual length? You can simply multiply this one by 8, and you'll be getting your answer, which is 28. You can write to 1 decimal place 0.0, or you can leave till here. Over to the next one. The student gives a bulb a small displacement and relays it so that it swings backward and forward. Figure 2.2 shows one complete oscillation of the simple pendulum. Okay, the student measures the time t for 20 complete oscillations because it's very difficult to measure the time of one oscillation accurately. There would be a lot of error in that. The time t is shown on the stopwatch in figure 2.3, as you can see on the diagram. Write down the time t. So how many seconds do we have? 21 complete seconds, and then after decimal we have 21. So 21.21. We have that many seconds on the stopwatch. Then we have the next one. The student measures the time t for 20 oscillation twice more. These readings are shown 21.30, 21.28. Find the average time for 20 oscillations of the pendulum. So you were having three readings, 21.21 plus 21.30 plus 21.28. You have these three readings, and you divide all three of them by the number of reading. The sum of these three divided by the number of the readings. And before you sort it out on the calculator, make sure you're writing the brackets or you're inserting the values in the decimal in the fraction mode, because otherwise only the last term 21.28 would be divided by 3, because calculator would tend to follow the BODMAS rule. If you write it without the brackets, calculator would calculate this one first and then add the remaining values. Then we have the next one. The period t is the time for one complete oscillation of the pendulum. Calculate the time period t. So we have the average time for 20 oscillation, which is 21.26, and that is the time period of 20 oscillations. We can divide it by 20 like this, and we'll be getting the time for a single oscillation, and that would be the time period capital T. Even the next one, that is of 2 marks. Calculate a value of g, the gravitational acceleration. Use the equation below. Equation is also there. Give your answer to three significant figures. So we write it as 11.1 divided by capital T. We have the value of capital T as 1.06. So I'm going to write it over here, 1.06, and the square of it, 9.87. So we have written the answer to three significant figures. Okay, so there are two decimal places, but there are three significant figures. Anyway, moving on to the next part. To find the period t of the pendulum, the student first measures the average time for 20 oscillations, which is a method that he should be doing because it would be very difficult to find the period of a single oscillation. Suggest why the student did not choose to measure the average time for the first one is only 2 oscillations. So why is he choosing to measure the time of 20 oscillations and not 2 oscillations? So the reason is same. For what reason you are not going to measure the time of 1 oscillation, the same is the reason for not measuring the time for 2 oscillations or any small number of oscillations. And that is, in that case, the chances of you being subjected to the human reaction time error are very significant. So the human reaction time error is significant if you choose to measure the time period of only 2 oscillations. And then he asks you, alright, so you're not measuring the time for small number of oscillations, But why are you not measuring the time for 200 oscillations? That is not a small number of oscillations. So what is the problem with measuring the time for 200 oscillations and then dividing the total time by 200? The thing is, if you try to go for 200 oscillations, your pendulum may not be even taking 200 oscillations in the first place. It might have stopped till like 30, 35, 40 oscillations, and that would be it. And if you're taking a time for 200 oscillations, the chances are you may be messing up with the number. You may lose the count. Once you're doing that, you would not be actually dividing by the exact number of oscillations. So 200 oscillations would be difficult for you to be concentrated till 200 oscillations. So it's better we don't take any dramatic number of oscillations. 2, 3, that is also dramatic, but at the same time, anything above 30, 40, 50, that is also very dramatic. Alright, so let's move on to the next one. Question number 3. A student uses a ray box to investigate the refraction of a ray of red light as it passes through a semicircular glass block. He sets up the apparatus on the sheet of paper as shown in figure 3.1, and then you can see the figure as well. The first one is measure the angle of incidence I of the ray at the point M. So we have to draw the normal at the point M, but it is already drawn. This is the incident ray. All we have to do is to measure the angle between the incident ray and the normal. What do we do for that? What do we use for that? We use a protractor, and we simply find the time period. We simply find the angle. Why did I say time period? The actual paper, it is 34 followed by the unit. Okay, the unit of the angle is degrees. It has to be written there at the top. Many of the students forget to write the unit. Without the unit, you won't be getting marked for this one. Okay, the angle of refraction at M is 22. This is already given. They have given you that the angle of refraction is 22. And you see, if you try to recall your concepts of this chapter, you realize one thing. When the ray of light enters a dense medium, for example, the ray of light enters from air into the glass, it bent towards the normal, and thereby the angle of refraction would be decreased. So the angle of incidence was 34 and the angle of refraction is 22. It is smaller than the angle of incidence. This is consistent with our understanding of optics. Okay, so figure 3.1. On figure 3.1, draw the refracted ray inside the glass block. It has to be drawn at the angle of 22. The compass may not be showing to you, but I'm drawing it at the angle 22. Okay, so here we have the angle 22. This is your refracted ray at the point M, and this angle R is representing the angle of refraction, and that is 22. So done with the first part. Label with the letter N the point where the refracted ray leaves the glass block. So it leaves the glass block at this point. And by the way, I've not extended this line over here because we don't know if it should be bending away or it should be emerging out straight, because it might be emerging out straight if this angle is 90 degrees. Otherwise, it would be bending away from the normal. So we can't say anything right now. So part C. The ray emerges from the glass block at N without further deviation. Okay, so they have stated this. What does that mean? The light ray is now merging out without any deviation in the angle. Draw the path of the ray as it leaves the glass block. Okay, so we can extend the same one. So without any deviation, that means the angle of incidence at n would be 90 degrees, or that angle would be 90 degrees. So straight line continued beyond the glass block. Okay, and then what do we have? So the next part says, done with this one, the next part says, describe how the student uses optic spins to mark the path of the ray accurately. I mean, we do it in the science lab as well. We always do these kind of experiments. The thing is, using the optic spins, what you have to do is you have to place the pins in the path of the ray, and once you're done with that, those pins, once you take them out, those pins will leave behind the pinholes, okay, the small little holes, and then you join those holes with the help of a ruler with a straight line. So place the pins. I'm writing the steps here. And one of the method by which you can improve the accuracy, to be on the safe side, the separation between the pins, once you're placing the pins, so the separation between the pins has to be at least 5 centimeter. The distance between the pins, or the pins should be at least 5 centimeters apart, and thereby the 2 points or the 2 pinholes that you'll be getting would not be very close to each other, and you'll be having a good approximation of the path, so with a straight line. So here we have question number 4. A student uses a thermometer to measure the temperature of the hot water as cool downs in a beaker. Explain why it takes the following steps to ensure that the values are accurate. Number 1, part A. It makes sure that the thermometer bulb does not touch the sides of the or the base of the beaker. So the thing is, we're trying to measure the temperature of the hot water, and we should be dipping the thermometer directly in the hot water. The sides of the beaker or the base of the beaker might not be at the same temperature as that of the hot water, because the thermal equilibrium state might not have reached yet. So the sides or the base of the beaker might be at different temperature. Alright, moving on to the next one. He stirs the water each time before taking the reading. Alright, this one is very recurring question. The simple answer is to ensure that the temperature of the water is uniform. Alright, so the last part of this one, he takes the temperature reading by viewing the scale on the thermometer at the eye level, perpendicular to the scale. Okay, and then what was the question? Why he takes the following steps to ensure that the values are accurate. Okay, so this one is basically to avoid the parallax error. We do this thing. To avoid the parallax error, the line of sight has to be perpendicular to the reading.